if you have two objects at different temperatures and they're in contact with each other, I think we all understand from life experience that heat will flow from the warmer one to the colder one, right? And that will keep happening until they both get to the same temperature. The amount of energy, heat energy, lost by the hot one has to equal the amount of heat gained by the cold one, assuming we don't lose any to the surroundings. Hello? So if we define one substance as the system and the other as the surroundings, we can say that Q for the system is equal to negative Q for the surroundings. And again, that doesn't mean that Q surroundings is negative or positive necessarily. It means that these two values are opposite in sign. It's like exchanging money, right? I give you $10, that's negative for me but positive for you. So we can look at, say, a hot block of metal in some room temperature water. So here we have some metal. It was at 55 degrees Celsius, and we're putting it in a beaker of water at 25 degrees Celsius. The metal is hot. It's going to transfer heat to the water and cause the water to warm up, right? How much is it going to warm up? Well, it's going to depend on several things. Depends on the mass of the metal and the mass of the water. It will also depend on the specific heat capacities of the metal and the water. But we can say the heat lost by the metal is equal to, but opposite in sign, to the heat gained by the water. Well, Q for the metal is the mass of the metal times its specific heat capacity times its change in temperature. And that will equal -1 times, might be easier to understand if we go like this. The mass of the water times the specific heat capacity of the water times the change in temperature for the water. Remember that change in temperature is the final temperature minus the initial temperature. One of these substances is getting warmer. Its temperature is going up. It has a positive delta T. The other substance is getting colder. Its temperature is going down. It has a negative delta T, right? So one of these is negative and one's positive, and so we need that minus sign in there so the signs work out okay. So let's do an example. A block of copper of unknown mass has an initial temperature of 65.4 degrees Celsius. The copper is immersed in a beaker containing 95.7 grams of water at 22.7 degrees Celsius. When the two substances reach thermal equilibrium, the final temperature is 24.2 degrees Celsius. What is the mass of the copper block? Why don't you just put it on a balance and weigh it? Wouldn't that be so much easier? Okay. We can do this. So let's highlight the numbers with their units. There's a whole bunch of them here. And then ask yourselves, okay, well, what are we trying to find? We're trying to find the mass of the copper block. So this is another one of those times when an ugly picture can be helpful. There's my beaker. There's water in it. Apparently there's some sort of disturbance happening in there. And here's my block of copper metal. Okay, so the block of copper metal was put into the water. And so we've got things like temperature and mass here, and we're asked for a mass, and we've got we're reaching thermal equilibrium. So this should make us think, oh, we're probably going to need to use Q equals mc delta T. Q equals mc delta T. And the other important thing to recognize is that Q for the copper will equal -1 times Q for the water. The heat lost by the copper is gained by the water, right? Okay, so let's identify what some of these things are. So the 65.4 degrees, is that referring to the copper or the water? That's the copper, right? So, and is that an initial temperature, a final temperature, or a change in temperature? That's the initial temperature. So the initial temperature for the copper is 65.4 degrees Celsius. I'm going to use colors instead of subscripts because I can. And then we have this, the next number here, 95.7 grams of water. Well, that's going to be a mass, right? And that's the mass of the water. So we'll do that one in blue. So the mass of the water is equal to 95.7 grams. That much water at 22.7 degrees Celsius. So is that, what's that? That's the initial temperature for the water. Okay, so T initial for the water, 22.7 degrees Celsius. When the two substances reach thermal equilibrium, the final temperature is 24.2. Well, obviously that's a final temperature, because it says that. Is that the final temperature of the water or the copper? Both, right? Because heat flows until they come to the same temperature. So at the end here, I didn't really leave much space here. The final temperature for the water is 22.4 degrees Celsius. And the final temperature for the copper is 22.4 degrees Celsius. Except I copied that down wrong, didn't I? Yeah, anytime, you're doing a problem and checking an answer and you're like, wait a minute, that's off. Double check that you started with the right numbers, because it's really easy to mess them up. Okay. And we're trying to find the mass of the copper, right? Yeah.
Where does the 22.4 come from?
I did it again. There's 22.4 liters per mole of gas. Does that have anything to do with this problem? No. Apparently my subconscious thinks that it does, but thank you. Let's see if I can write it down correctly. Okay, so we've identified the numbers that we've been given and what we're trying to find, and we identified equations that we're going to be using. What is missing? Yeah, specific heat capacity. We don't know, the specific heat capacity wasn't given here, and we also don't know Q. But what we're going to do here, Q for the copper is equal to negative Q for the water. So we can say that the mass of the copper times the specific heat capacity of the water times the change in temperature for the water is equal to -1 times the mass of the water times the specific heat capacity of the water times the change in temperature of the water. And we actually don't need to know the value of Q because these two things are going to be equal to each other. Where do we get specific heat capacities? From the chart, from the table. So let's go back to that. There we go. So copper was 0.385. The units are joules per gram degree Celsius. And water is 4.18. 0.385. So the specific heat capacity for the copper is 0.385 joules divided by grams degrees Celsius. Specific heat capacity for the water is 4.18 joules per gram degrees Celsius. So we have the mass of the water, we have the specific heat capacity of both of these. We've got a whole bunch of temperatures, but we don't have the change in temperature, right? So let's calculate that. So the change in temperature for the water is the final minus the initial. The final is 24.2. Got it right that time. Minus the initial, 22.7. So that's 1.5 degrees Celsius. And the change in temperature for the copper is its final temperature. Okay, so we looked up the specific heat capacities, we calculated the change in temperature for each substance, we rearranged our equation for the value we want to find, and we plugged the numbers in here. Let's look at the units before we do any calculations. So I have grams here, and there's grams down here, but there's also these guys. Here we got joules per gram degree Celsius, joules per gram degree Celsius. These guys are going to cancel all of those guys. So this one cancels that. And here I've got degrees Celsius, and those are going to cancel. And that leaves me with gram, which is good because I want a mass, and gram is the unit for mass. When you do this on your calculator and you're dividing down here, use your parentheses if you're going to do it like that, okay? There's other ways on the calculator, and if you're interested in that, I'll show you. But I'll just talk you through what I'm doing here. I'm going the change sign, negative 95.7 times 4.18 times 1.5 divided by, open parentheses, 0.385 times negative 41.2, close the parentheses, and I'm getting 37.8. How many significant figures should this answer have? 3 is a great guess. It's actually only 2 for this one. Would writing 3 down really hurt anything? No, it really wouldn't. So if you did 3 sig figs and came up with 37.8, and this was a multiple choice question, you're not going to see 37.8 as one of the choices. You would see 38 grams. And so that it's important to recognize that this rounds to that. Any questions? Did your calculator do the math okay for you? Let's get back where we were. Oh, see, the book says 37.8. They overlooked the 2 sig figs in the delta T. Again, not the end of the world. Pressure volume work. This happens when a force that is caused by a change in volume acts against an external pressure. So we defined work as a force acting through a distance. And so that's what's happening here, but it's a special kind. So here we have a piston, say, like you might find in an internal combustion engine, which is called that because combustion happens in the internal parts of the engine. So initially the piston is down, there's gas in here, little explosion from the combustion happens, and the volume changes. That exerts a force on the piston and moves it up. The piston is being opposed by atmospheric pressure. So whenever gases expand, the change in volume is positive, right? Because it's getting bigger. But the system is doing work on the surroundings. And when we do work on someone else, it's kind of a drag for us. It's kind of negative, right? So for the gas, then the work is negative. So how do we make that work out? No pun intended. W equals -1 times the external pressure times the change in volume of the gas. Here's a new conversion factor that you do not need to memorize, but you need to know that it exists. 101.3 joules is equal to 1 atmosphere times liter. So the units we could end up with here, pressure in atmospheres, change in volume in liters, right? Atmospheres times liters. How is that units of work? Well, this is equal to this many joules. So a cylinder equipped with a piston expands against an external pressure of 1.58 atmospheres. If the initial volume is 0.485 liters, the final volume is 1.245 liters. How much work in joules is done? So we read the problem, we highlight the numbers, we highlight the question. Work in joules. Okay, so it says that 1.58 atmospheres is an external pressure. So P, EXT, that's our pressure. We have an initial volume, we'll call that V initial, I for initial, 0.485 liters, and a final volume that's 1.245 liters. How much work is done? So we need the equation. Work is equal to negative external pressure times change in volume. So we have the external pressure. We don't have delta V, but we can calculate it easy enough, right? The change in volume will equal the final minus the initial. So the final is 1.245. The initial is 0.485. .76. For sig figs here, I'm subtracting, and this has 3 decimal places, and that has 3 decimal places. This answer should have 3 decimal places. The calculator doesn't show me what's over here because it's nothing. But I'm going to put a 0 there because I know there should be 3 significant figures. So that's a change in volume. So work is equal to -1 times the external pressure times the change in volume so -1.2008 atmospheres times liters. They want the answer in joules. Well, we just learned about that one. This guy right down here. 1 atmosphere liter is 101.3 joules. So I can convert that. I want joules on top, atmosphere liters on the bottom. We looked it up. It's 101.3 joules for every 1 atmosphere liter. So this is going to be -121.64 joules. Should be 3 sig figs, so -122 joules. The gas is doing work on its surroundings by pushing out that piston. Any questions? Here's another question about pressure volume work. When fuel is burned in a cylinder equipped with a piston, the volume expands from 0.255 liters to 1.45 liters against an external pressure of 1.02 atmospheres. In addition, 875 joules is emitted as heat. What is delta E for the burning of the fuel? Well, let's highlight our numbers. And highlight the question. What is delta E? So those first 2 are volumes going from the first one to the second one. So the initial volume is 0.255 liters. The final volume is 1.45 liters. We're given the external pressure as 1.02 atmospheres. And 875 joules. Emitted as heat. What variable do we use for heat? Q. I know it doesn't make much sense, does it? H is busy doing other things. So Q is heat. And then we have to ask ourselves, is this positive or negative? Sometimes the words in the sentence tell us what direction it's going. Other times we have to use plus and minus signs, right? So an example in money is, if I paid $10 for a Dutch Bros coffee, I don't even like coffee. If I paid $10 for it, I wouldn't say that I paid negative $10, right? But what's it going to show on my account? It's going to show negative 10 because 10 went out, right? But when I say I paid, that tells you that the money left me. So here, this is telling us that that was emitted as heat. So for the system, is this positive or negative? Emitted, going out. It's going to be negative. Just like money going out of your possession, out of your wallet, your account, whatever, it's negative. Coming in is positive. Okay, so we've got all of these things. And it's saying, what's delta E? Oh my goodness, delta E? That was many slides ago. Well, there was actually quite a simple equation. The total change in energy, internal energy for something, is equal to the heat plus the work. So I need to know what Q and W are. I already know what Q is. How do I find work? Well, that's the equation we just learned about. Work is negative P external times change in volume. I got the external pressure. I need the change in volume. So delta V, 1.45 minus 0.255. $1.195. Well, let's calculate the work. So the work is equal to negative times the external pressure times the change in volume negative 1.2189 atmosphere liters. To find delta E, I need to add Q and W. Here's Q, and here's W. Can I add joules to atmosphere liters? No. No, I can't. We're going to have to convert this to joules. So we go back and look at the slide. 101.3 joules is equal to 1 atmosphere liter. So I wasn't keeping track of my sig figs. Here when I'm subtracting, I'm going to try again with that 1. Wasn't very nice. It's a 1. 2 decimal places, 3 decimal places. So this number ends in the second decimal place. So then over here I have 3 sig figs and 3 sig figs. So this should have 3 sig figs. So now I can say, well, delta E is equal to Q, negative 875 joules, plus W, negative 123.47 joules. Negative 998 joules. Any questions? This is not the kind of calculation that we do very often in chemistry. We're doing this here more to understand about how energy is transferred between things. Negative 998.